Ladies and gentlemen, class recording has started. Carrots. Carrots. Are we going to a different vegetable every day this week?
No, because it was watermelon the first time.
Different produce. Okay. All right. Yesterday we discussed the ideas of the black hole, and we came to the conclusion that according to Newton's interpretation of gravity, light wouldn't get sucked into a black hole. Because Newton's interpretation of gravity says that gravity exists between two masses, and light is energy. It doesn't have mass, so it shouldn't be affected by gravity. Yet, we have evidence to suggest that light is affected by gravity. So we had to come up with a new understanding of what gravity was. And that new understanding of what gravity was provided by Newton. Not Newton, Einstein, sorry. So Einstein comes up with this idea, and I believe yesterday we sort of talked about the trampoline, right? We remember our representation of the universe as a big trampoline, and then as we set things onto the trampoline, it creates dents in the trampoline. Does this sound familiar? Hopefully not as far. And that gravity really is just objects that move along the surface of the trampoline, and then when they encounter one of the dips in the trampoline, they fall into the dip. And the bigger the mass something has, the bigger the dip it makes in the trampoline. And that would explain a black hole in that it's a hole that is so deep, a dip so deep in the trampoline, that even if I'm standing at the bottom of the trampoline, and I take this red ball and I throw it upwards with the speed of light, guess what? I don't throw it fast enough that it would get high enough to get out of the dip of the trampoline. And that's our explanation of a black hole. Okay? Is that good as far as a quick review of yesterday? This idea of the universe existing as a quote-unquote trampoline, okay? And yesterday I sort of mentioned, I think it was Devin, I can't remember, but this is a two-dimensional representation of a four-dimensional idea. And so we're going to throw in a fourth dimension here in just a second, and hopefully your head hurts already because, right? Yeah, so. Yep. All right. This idea of the trampoline comes out of Einstein's theory of special relativity.
What makes it special?
It's special because this part of Einstein's theory only applies to things that are in what he referred to as an inertial frame of reference, no acceleration. It's either standing still or it's going constant speed. Tomorrow we will talk about Einstein's theory of general relativity, which applies to all things. Okay? So Einstein comes up with this idea of special relativity. Okay? Now, when he does this, okay, he's not some glamorous scientist, he's not Einstein, right? He actually works in a patent office in Switzerland, and he's Einstein working at a patent office, so he basically gets all of his work done before lunch, and then after lunch he just sits around and thinks about stuff. And what comes out of his thinking about stuff is a completely new way that we interpret the universe. Okay? That's all. So, this idea of understanding the universe starts with Galileo. And Galileo kind of introduces us to the idea of inertia, that things don't want to slow down, which was the prevailing thought at the time, that really things will do whatever they were currently doing unless something makes them stop. That idea starts off with Galileo. He calls it inertia. Newton then takes all those ideas from Galileo and puts together these three bad boys, which I think we've, by now, I said, just in case you forgot, although I hope you won't be able to forget at this point in time, okay? So 1, 2, and 3, right? And then he throws in gravity on top of that. And so if you want to think about it as a fourth law, you can as well. But that does a really good job of pretty much explaining every motion, every mass interaction that we knew about at the time. And it continued to explain every mass interaction up until about 1900, about the time of Einstein. Okay? Newton takes care of mass. This guy, who we haven't learned about yet, and we're not going to talk about him a whole lot, his name is James Clerk Maxwell. He takes care of light. In 1864, he publishes a paper, and he has 4 equations. And those equations have all kinds of integral symbols in them, and it's messy calculus stuff. But his equations explain the behavior of light and other kinds of electromagnetic radiation, or energy. Newton explains mass, Maxwell explains energy, and about 1900, that's it. We've got the whole universe figured out. Okay? Newton explains mass interactions, Maxwell explains energy interactions. Mass and energy are all good, everybody agrees, shake hands, let's go figure out something else. Except for this. Okay. These two guys, Albert Michelson and Edward Morley, in the late 1800s, performing this experiment close to this area here at Case, okay, do an experiment dealing with light. Okay? First, a side note. I went to Case. I think we've discussed that before. If we haven't, I went to Case. And the dorm that I lived in, Glazer Hall, was right next door to Michelson Hall. Okay? Those guys were jerks, right? Jerks. Right? But we always used to beat them in like dorm Olympics and stuff, so that was good for us.
Wait, those two were jerks? Or like
No,
the hall itself?
the people that lived in Michelson Hall, which was the dorm right next to mine,
Oh, okay.
those guys were jerks.
You went to school already?
Just
Not what
because they,
meant.
I mean,
just meant, like,
basically because their guy, I don't know, their guy like reinterpreted physics for everybody. I don't know, they had some kind of like God complex about it or something, or I don't know. Or maybe they were just jerks. They decided to put them all there. So, but anyway, not all of them, okay? I'm stereotyping, but
Generalized.
a lot
I'm
of them.
sure on the
A lot.
survey. Are you a jerk? It's
So,
like
did
the one
you
who
go to
checked yes.
Michelson Hall? Yeah, it's on the application. So, are you a jerk? Check Michelson. Go. March up that hill and go put your stuff in a room. So it's not top of a really big hill, but anyway. All right. So here's the problem. At the time, we know light to be a wave, but the way that we knew that waves worked was that they had to travel through something. They had to travel through a medium. Theoretically, they called this medium the luminiferous ether, and that there was no such thing as a vacuum. That there was the sun and its mass, and then there was the earth and its mass, and all of this space in between that was filled with this mysterious ether. And the light traveled through that ether, and that's how light got from the sun to us, even though it appeared that there was nothing there. So, Michelson and Morley are trying to do experiments to prove the existence of this luminiferous ether. Guess what? No ether. Okay? They find no evidence to suggest that there is anything that fills the space between us and the sun. But they make measurements of the speed of light. And that speed of light always comes out exactly the same speed. Which is good, because as we've discussed, the speed of light is constant. It's 3.0 times 10 to the 8th, and that's an established fact. But there's a problem. And the problem deals with this picture. So if you're here on Earth, and you stand on the back of, here, let's do this. Spotlight here. So if you stand on the back of a truck, I don't condone this, it's dangerous, but if you stand on the back of a truck, and let's say you throw a ball to your friend, and you throw the ball at 50 miles per hour, how fast is it going to be going when your friend catches it?
Less.
A little less because of air resistance, but let's say it's pretty small air resistance. So if you throw it at 50, your friend catches it at, let's go 50. Let's make it nice and easy, okay? All right. But here, in the second picture, now you're standing on the back of the truck that is driving towards your friend at 20 miles per hour. Granted, let's assume that it stops before it run your friend over, just to get that out of everybody's head, because I know some of you are thinking, like, well, that guy's going to get run over. It stops.
Like you run over before or after you
But let's say it stops, and he never gets run over. Okay? At least not in this picture.
But
You may
the
get,
guy will fly right into him.
well,
It
yeah,
stops.
yeah, it stops. And he's got special magnetic boots to hold him onto the truck. So, truck is moving towards its left, our left, okay, backwards as it is in this picture, at 20 miles per hour. This guy, the guy in the blue, can still throw the ball at 50 miles per hour. Red guy is going to catch it with what speed? Faster. If this is 50, this is 20, he's going to catch it going 70. Okay? But in the bottom picture, now that same truck is driving away from the red guy at 20 miles per hour. Blue guy still throws it. Here, let's zoom in a little bit. Blue guy still throws it at 50 miles per hour, but now he's on the truck that's moving towards your right at 20. How fast is it going to be going when red guy catches it? 30. Right? Does that make sense? Okay? Depending on how he's moving, that's going to affect the speed that red guy catches the ball. Okay? Everybody knows that. We measure it, it's great. All works. Okay? Except when you do it with light. Alright, so let's zoom in here a little bit. Okay? So, here's a flying flashlight. How is it flying? I don't know. It is, though. Okay? As it's coming towards this guy, okay, light travels at a certain speed, 3.00 times 10 to the 8 meters per second. As this light is traveling towards the guy in the red shirt, guess what he measures the speed as? 3.00 times 10 to the 8th. The fact that this flashlight is coming towards him doesn't speed up the speed of light. Here, the flashlight is moving away from him. In the old example, that slowed down whatever we threw. But if we throw light back towards this guy, he still measures it traveling exactly the same speed, 3.00 times 10 to the 8th. Here, he's on a rocket ship heading towards the flashlight.
It's a very fast flashlight.
Yeah, it's a real fast flashlight, totally. All right, but here, like when you ride the Rapid or some other kind of train, or if you're in a car and you pass another car going the other direction, it looks like that other car is going much faster, right? Because you're coming towards it, it's coming towards you. You perceive that car or train or whatever it is to be going much faster than it actually is. Not the case with light. In this case here, if we flip on this flashlight and he measures the speed of light, guess what? Exactly the same. This is what Michelson and Morley find out from their experiments. That if you go back and look at their picture, here, hold on. At different times of the year, Earth is moving towards certain stars, and in other times of the year, it's moving away from certain stars. But guess what Michelson and Morley measure about the speed of the light coming from those stars? Always the same. It never changes regardless of the motion, which is a problem, because that's not what Newton said should happen, but it does. Alright, so, okay, we always measure this light to be the same thing. So what does that mean? We have a theory of the universe that Newton put forth about 350 years before this happens, and it's worked great up until that time. But now it doesn't work great. So if you got an explanation that doesn't explain stuff, what do you got to do? You got to come up with a new explanation. You got to make something up, right? So who makes something up? Newton. No, Newton's been dead for 350 years. So okay. Okay. Who makes something up? Einstein makes something up. Why? Because he has to go up and screw up our perfect physics world. But it wasn't perfect physics world, right? We couldn't explain something. So he has to come up with something else. Okay? All right, ready? Deep breath. Einstein starts messing around with this idea of, well, what is space and what is time? These are things that we take for granted. Our Earth is a certain size, it exists in space, that space, or it's a certain distance away from the sun, blah, blah, blah. Based on how quickly light travels, we can figure out how much time it takes for that light to get here to the Earth, blah, 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 blah. These are things we take for granted. But Einstein says, no, it's not really like that. We take it for granted because of the situation that we're in. But in reality, space and time are something completely different from what we think of them. Okay? Go
I
ahead.
had a question about like the star thing.
Go ahead.
How, if they didn't know the speed of light yet, how did they know how far away the stars
No,
are?
they did know the speed of light. Maxwell's equations come out in 1864. That was like 1887.
Oh, so they didn't know.
Yeah, that was, and actually before that experiment, Michelson was the one who actually figured out the speed of light. So in a previous experiment, he figures out how fast light is going.
Well, then wouldn't he know that it's constant anyhow before he even did that experiment?
No, he would know it's constant, but Evan, I could set the cruise control on a car driving out there on Hilliard Boulevard at 35 miles per hour. But based on where I look at it from, it may not look like it's going 35. You know what I'm saying?
Yeah.
Like it's 35 if I'm standing on the side of the road. But if I'm in a car behind it going 35, that car's not moving. It stays exactly the same speed in front of me. But if I'm in a car on the other side of the road going 35, now that car looks like it's going 70 because it's coming at me real fast. But what Michelson and Morley figure out is that it doesn't matter what I'm doing. That car, I would always measure it at 35 miles per hour. Does that make sense?
Yeah, I get it.
Well, it probably doesn't make much sense, but that's what they found. That how you look at the speed of light does not affect the measurement of its speed. It's always the same.
Okay.
Okay? There is no such thing as relative velocity or relative motion when it comes to light. It's always the same number. Okay? So, because the speed of light is a speed, it deals with distance, it deals with time. So Einstein starts thinking, re-examining what is our perception of space? What is our perception of distance? What is our perception of time? And he comes up with what we thought it was really isn't what it was. Einstein proposes that the universe consists of this thing that he calls space-time. Pretty inventive, I know. It's pretty, he probably thought long and hard about what to call this thing, you know. Yep. Space-time is the trampoline that we talked about yesterday in class. The surface of the trampoline is not a constant thing. It can change depending on the conditions. The universe changes depending on the conditions. But it takes into account not just the x-axis, not just the y-axis, not just the z-axis, but now it also takes into account the t-axis, the time aspect of it all. Whereas before, most of us think of time as a continuous thing, right? A second is a second is a second is a second. That's not what Einstein says. That time is also relative. Okay? You okay with that? Okay. All right. Here we go. So how does he prove it? Okay. In certain instances, you can travel through time without traveling through space. As you sit here right now, your life is wasting away, right? But you're not going anywhere. So, okay. As most of you most of you probably feel at this point in time. So I might as well have just spoken Chinese up here for most of that time, right? Okay. In certain instances, you can travel through time without traveling through space. Okay? Here, time goes on, but you're not going anywhere. In certain instances, you can travel through time and space simultaneously. As you drive in your car, time is going on, but now you're going somewhere. Go ahead.
Oh, wait, since the Earth is moving, are we technically moving
Yep.
through space?
Yes, and time. Okay?
Yeah.
Now, Rachel, that sort of gets us back to the relative sort of thing, that the way you perceive it is that you're moving through time but not moving through space. But in big picture-wise, we are actually moving through both space and time at the same time. That gets back to the relativity part. For matter, how we perceive it is a little different than light, and that's what we're going to see in just a second. Okay? Evan, go ahead.
Well, is it really possible to stand still if like the galaxy's spinning too?
Right, and that's what Rachel kind of said, that our perception of it is that we are moving only through time but not through space. Okay? Yeah.
Well, so do you think that's actually standing still?
No, not really. Right? So in actuality, everything is probably moving through both space and time at the same rate. I shouldn't say at the same rate, simultaneously. Okay? And that sort of takes into account this. Okay? But light, once again, light is different. Okay? Most of the motions that we go through, even our motion of the Earth spinning around the sun and the sun spinning around the galaxy, those are, in the grand scheme of things, very slow speeds. They're really fast for us here on Earth, but compared to light, really, really slow. Okay? But Einstein says, as you go faster and faster and faster, you move more through time and less through space. Oh, sorry, wrong way. Backwards. More through space, less through time. Here, you're moving through time and only time, relatively speaking. But as you go faster and faster, more of your motion occurs through space, but less through time. If you move faster, how long does it take you to get from your house to your friend's house? Less time, right? If you move slower, it takes you more time to go the same distance, right? Are we okay with that concept, at least for now? All right. So, what is space-time? What Einstein says is that light travels only through space, but never through time. Light is quote-unquote ageless. And here's how he rationalizes that. Okay? Einstein doesn't have a rocket, but he does have trains. Okay? So let's say you're sitting in the station on a train that isn't moving. Okay? You look at the clock. The only way you can see that clock is because light goes, bounces off of that clock, and comes back to your eye. Okay? That's how we see things, right? Light bounces off that clock, 11:38, back to you, 11:38, back to you, 11:38, back to you, 11:38, back to you. Always 11:38 until it switches, and it goes to 11:39. Okay? Now, as you take off out of the station, you're moving much slower than the light coming off of that clock is moving. So as you pull out of the station, you still perceive the clock to say 11:38, because the light off of that clock gets to you like this. But how far does that light have to travel as you move farther and farther away from the station? How far away are you from the clock? You're farther from the clock, right? So if light has a farther distance to go, but it travels the same speed, how long did it actually take to get to you? Longer than when you were sitting in the station. Now, let's say you could be on a train that goes really, really, really fast. Like 3/4 of the speed of light. This light bounces off the clock. It says 11:39. It's coming toward, or it's trying to run you down, but now you're on a train going 3/4 of the speed of light. Is it going to get to you in 1 second? This clock may have already switched over to 11:40 by the time the 11:39 light gets to you. Does that make sense? Okay. But what do you see the clock as? 11:39, because the 11:39 light is just getting to you, but this clock switched a minute ago. So what's the time? Not to you, it's not. To you, it's 11:39. To people still standing. Say again?
That's why they put clocks on trains.
Exactly. Okay. So that's the next. That's one of the next slide. Okay. But now let's say you're going in a train that is traveling the speed of light. the light from the clock that said 11:39 gets to your eye at the exact moment that you go the speed of light. Now, you're seeing the clock as 11:39. It's switching, right? It's going to 11:40, 11:41, 11:42, and light is bouncing off of it, but does it ever catch you? Because you're going the speed of light. What would you see the clock as? 11:39, forever. Okay? Light travels through space, but never through time. And if the closer you're going to the speed of light, the more you travel through time. Sorry, the more you travel through space and less through time. Okay? Einstein's really fast trains. Okay? Does that make sense? And this is how Einstein sort of started rationalizing things. And he comes up with two postulates, which are just fancy names for rules. Okay? So, postulate number one of Einstein's theory of special relativity. All laws of nature are the same in all uniformly moving frames of reference, or what he refers to as inertial frames of reference. Okay? Well, that's a fancy way of saying there is no experiment that I can do to prove that I'm moving and somebody else is sitting still, or somebody else is sitting still and I'm moving, as long as we're both constantly going the same speed. Example. So here is a man shaped like a billiard ball playing billiards. It's ironic, okay? But if you're on a cruise ship, okay, if you're on a cruise ship or a plane that is traveling at a constant speed, you've reached cruising altitude on your plane, or the boat has reached cruising altitude, what does that feel like to you? Does it feel any different than you sitting here at rest in this room? If you could write things down, if you so chose to listen to this lecture on a transatlantic flight, perhaps you need some rest, I don't know, or if I take this ball, right, in the room, I throw it up and I catch it just like this. If I'm on a plane that's going 500 miles per hour, as long as it's not speeding up or slowing down, I take this ball and I throw it up in the air, where does it land? Right back in my hand, just like it did here when I was standing still. All right?
And that's disregarding air resistance.
That's disregarding air resistance, as long as there is no acceleration. Okay? So acceleration changes that whole thing. Okay? But that's why this is special relativity, because it's not accelerated. Okay? Or think about when you're at the light at an intersection and you have your foot on the brake, but that car like creeps up in front of you, right, or creeps up next to you, and it feels like you're moving backwards, right? And you push your foot down harder, even though your foot is already on the brake, right? Okay. Never. Come on.
I don't.
Come on. For real. Never.
It's some prank, Julie. What's the?
Not me.
But there, right? You're sitting still, and that car is moving. But you can't determine whether you're sitting still and that car is moving, or whether that car is sitting still and you're moving. That's what Einstein says, is that all the laws of physics are exactly the same as long as we're moving at a constant speed, or not moving at all. What he refers to as an inertial frame of reference. Okay? Good there? Rule number one. Okay. Rule number two. The speed of light is always the same, regardless. Source of the motion, source of the observer, which is what Michelson and Morley found in their experiment, but Newton turns into a law. Okay? And he uses this law to explain the ideas of special relativity. Okay? Are we good with some conceptual base? Okay? Now, let's take a look at some numbers. The idea of time dilation. Okay? All right. So, here is a guy sitting in his own special spaceship. Okay? And this yellow line represents something that we refer to these relativity circles as a light clock. Okay? It's a little pulse of light. This pulse of light goes up, it bounces off a mirror on the ceiling, and it comes right back down, and it lands right where it started. Okay? If this spaceship is sitting still, this guy would see the light go up, bounce off the mirror, and come back, right? If this spaceship is traveling at 800,000 miles an hour, as long as it's constant 800,000 miles per hour, he would see the light go up, bounce off the mirror, and come back. Right? Does that make sense? Just like me throwing the ball up in the air. And if this keeps happening at a regular interval, he would just see this thing go up, bounce, come back down. Up, bounce, come back down. Up, bounce, come back down.
Since it's going so fast, why don't we just...
Sure. I mean, well, if he's moving along with this, all he sees it go up, come down, go up,
I mean,
come
like
down.
the light, because it would be like bouncing so fast.
Yeah, I mean, it's obviously a hypothetical situation, but Rachel, because this light travels at the same rates, yes, it would be a very small interval, but that interval would not change. Does that make sense? Okay? And that's regardless of whether he's moving or whether he's not moving. Good? All right, next picture. The next picture shows this girl. And she sees that light moving too. It's a glass spaceship. I should have explained that earlier. It's a glass spaceship. Okay? She sees the pulse go up, bounce off the mirror, and come back down. But did it go straight up and down to her? No. But what has to be the same in both instances? The speed has to be the same. Speed, let's do this. Let's take this. I could just do this. Where they're already on the same picture. Wrong one. There we go. Speed is a relationship between distance and time, right? Speed is a relationship between distance and time. Okay? But, according to Einstein's postulate, this speed and this speed have to be the same. Right? But, what would the distance be? Which one sees, do they see the light pulse traveling the same distance? This guy sees the light pulse go up, bounce off the ceiling, come back down. This girl sees the light pulse travel this real big diagonal path. If speed has to be the same, but the distance for her is greater than the distance for him, what has to be true about the time?
Us.
Nope. If this is bigger for the girl, but the ratio has to remain the same, time has to get longer. So if this guy measured this time that it takes to go up and down, Rachel, it's a real small interval, but he could measure it. The interval that she would measure it would be a longer interval. Let's say for argument's sake, this guy would measure the time that it takes for the light pulse to go up and down as 1 second. This girl would look at it and go, no, it's not 1 second, it's 2 seconds.
So it's like almost proportional.
Yes, because the speed has to be the same. If the distance, well, actually there's a ratio that I'll show you in a second. But the thing is, though, the biggest thing is it a different clock? No. It's the same clock in the same glass-walled spaceship. But the guy who's moving with the clock says it runs one rate, and the person watching the clock from the outside says it runs another rate. Space-time. Time is not a constant value. Time depends on where you measure it from. Same clock, 2 different observers, 2 different times. Alright? This idea of time dilation space. But the speed of light is not affected by the movement through time or space. So, clocks that are moving fast, we perceive them to run more slowly. But if you're moving with the clock, do you perceive it to be moving slowly? If you're with the clock, it runs exactly the same. If you're watching a clock move really fast, it moves slow. Now, does that mean as you're driving in your car, the clock on your dashboard runs slowly? Not to you, because you're moving with it. But if you watch the clock in the morning, by the time you get home at night, is it different than the clock in your garage or your house? It's been moving all day. Does it record a different time than the clock in your house? Yes. But how fast have you been moving all day in relation to the speed of light? You're not moving anywhere close to the speed of light. So does your clock slow down very much? No. Is this real? Yeah.
Wait, wouldn't like the delay only come from like how fast and far the light has, how far the light has to travel?
Yes.
So
Which is related to how fast the glass-walled spaceship is moving.
Right, but in your car, you stop your car and you're still reading your clock.
Yeah.
It's not moving at all.
But the point is, to you in your car, you never see a change in its speed because you're always moving with it. But your clock at home hasn't been moving all day, so those two clocks would read something different.
But only when one of them is moving.
Only when one of them is moving and one of them isn't, but that difference doesn't like go back once it's happened, you know what I'm saying?
Right, but I'm only perceiving the difference.
Yeah, but that's how you perceive it.
When I stop my car, the times are different.
No, actually not true. To you, it never changed. But to someone who was driving in your car earlier in the day, you dropped them off, you drove around some more, and you came back. Now your car, the clock in your car is different than their watch. Because your car has been moving around. Their watch hasn't been moving around.
Right, but when our car stops, when they go back.
No, the difference has already happened. It doesn't fix itself. They're back on the same rates again once they stop
this is
again,
already
but
sped
the
up.
difference has already happened and now they're off. Okay? Does this happen? Yeah, it happens. Back in the 70s, they put some really accurate atomic clocks on a bunch of airplanes. And they flew these airplanes around for months, hours of flight time, moving at what we perceive to be very large speeds, but in the grand scheme of things, not very large. Guess what? When they eventually got those clocks back off the plane, they were different than the clocks that were on the ground. How much? Not very much, but enough to match exactly what Einstein said they would.
What's a video?
That's the video clip that just kind of explains it, but it's like 5 minutes long, and the bell's going to ring in 2 minutes. So. All right, so chew on that for a little while. Then we'll come back tomorrow and explain some more mysteries of the universe and make your head hurt.
And then we'll have all spring break.
Yeah, and you have all spring break to digest. So you'll be on YouTube every night looking up videos on relativity.